Now in this video I'm going to derive Euler's formula using Taylor's theorem. Now this is Euler's formula: e to the power I theta equals to cosine theta plus I sine theta. Right, now I'm going to derive using these three expansion. These are the Taylor series expansion, and these two are the expansion of the sine x and cosine x, and this is the expansion of e to the power x. Now if you see, this is the Euler's formula. In the Euler's formula, it establishes a relationship between e to the power I theta, that's a exponential function, and a trigonometric function, that is the cosine theta plus I sine theta. Now we are going to derive this. Now before deriving this, you just see these three series. Well, e to the power x is equal to 1 plus x by 1 factorial plus x squared by 2 factorial plus x cubed by 3 factorial plus x to the power 4 by 4 factorial plus x to the power 5 by 5 factorial, and the series continues. The sine x is x minus x cubed by 3 factorial plus x to the power 5 by 5 factorial minus x to the power 7 by 7 factorial plus x to the power 9 by 9 factorial, and so on. That means it is x to the power n. So let's write it down. So sine series continues up to the sine series, let me write it down, continues up to x to the power n by n factorial. Right, so it continues up to x to the power n by n factorial, where x is an even, x is odd. So I'm not writing down because this is an infinite series. So it continues up to x to the power n divided by the n factorial, where n is an odd number. See, all are odd number. X to the power 1 by 1 factorial, that's an odd. X to the power 3 by 3 factorial, that's odd. X to the power 5 by 5 factorial, they are all odd numbers. And you see, the first term would have plus, then next minus, then plus, minus, plus, minus, plus, minus, and so on. So this would be minus actually. This would be minus, plus minus plus minus, it would continue. Now similarly, the cosine x is 1 plus 1 minus x squared by 2 factorial plus x to the power 4 by 4 factorial minus x to the power 6 by 6 factorial plus x to the power 8 by 8 factorial, and so on. So again, it's actually x to the power n by n factorial, where n is a positive even integer. Similarly here also it's a positive odd integer, and in both the cases n is not equal to 0. So let's just a revision. X to the sine x continues up to x to the power n by n factorial, where n is a positive odd integer and n is not equal to 0. And cosine x continues up to x to the power n by n factorial, where n is an even integer and of course n is not equal to 0. And of course they continue between the first term would have plus, then minus, plus, minus, plus, minus, and it would continue. Now if you see this e to the power x expansion, this term is very simple. This series is very simple, you can understand. It's 1 plus x by 1 factorial plus x squared by 2 factorial, and so on. So it's x to the power n by n factorial, where n is any positive integer and n is not equal to 0. So the e to the power x expansion was 1 plus x squared by 2 factorial, of course this by 1 factorial, x squared by 2 factorial plus x cubed by 3 factorial plus x to the power 4 by 4 factorial plus x to the power 5 by 5 factorial plus this is 5 plus x to the power 6 by 6 factorial, and so on. So that's the expansion of e to the power x. Now if you see, there is no negative term here. All terms in this expansion are positive. Now what I'm going to do is that I'm going to derive Euler's formula. So the right hand side had the right hand side had e to the power ix. So what I did, I replaced x as e to the power ix. So what I'll do in this term, in this part, this functions, in this function, is that I'm going to replace x, all the x, with ix. That is, I'm going to replace all the x with ix. That's ix to the power, I'm sorry, x by 1 factorial plus ix whole square by 2 factorial plus ix whole cube by 3 factorial plus ix to the power 4 by 4 factorial, and so on. Now one thing you need to note that I've shown in my previous videos, the powers of I. The first term, the second term contains I to the power 1. The third term contains I square. The fourth term contains I cube. The fifth term contains I to the power 5. The sixth term would contain, the fifth term contains I to the power 4. Of course, that's, I just made a mistake in saying. Now, and so on, this would continue. So I to the power 1 is obviously 1, is obviously I. And I square by definition is negative 1. I cube is negative I to the power 4 is 1. And then again, I to the power 5, the value of this starts from here, I. And then I to the power 6 would be this, negative 1. I to the power 7 would be this, negative I. And I to the power 8 would be this, negative plus positive I. So the value oscillates between I and 1. So it starts from I, then negative 1, then negative I, then 1. Again I, then negative 1, then negative I, then 1. So we can just substitute these values in this equation, e to the power ix, this expansion. So what I do is that I just write e to the power ix, and here I add 1 plus this 1 plus ix remains as it is, ix, because I to the power 1 is 1, so ix remains as it is, divided by 1 factorial plus I square x square, this is I square x square, so I square is negative 1, so negative 1 times x square divided by 2 factorial plus, see, I cube x cube is negative I, so it's negative I times x cube by 3 factorial plus I to the power 4, x to the power 4 is just positive 1, so it's x to the power 4 by 4 factorial, and then again the I to the power 5, x to the power 5, that I have not written here, but you can make out the values. Now it's just 1 plus ix by 1 factorial minus x square by 2 factorial plus minus I x cube by 3 factorial plus x to the power 4 by 4 factorial, and if I had a fifth term it would have I, so it would have I x to the power 5 by 5 factorial, and so on. Now if you see this term, it contains, see, it contains a real part, and then again a real part, and a real part, and so on. And it also contains an imaginary part. So it contains an imaginary part, an imaginary part, and an imaginary part. So it contains one real part, then an imaginary part, and a real part, and an imaginary part, and so on. So what we can do is that we can group the real parts, these real parts, and we can group the imaginary parts. So let's write them down separately. So I'm writing the real parts separately. That is, the real parts are 1 plus, this is the real part, x square by 2 factorial, and then this was the real part, x to the power 4 by 4 factorial, and so on. Then I have the imaginary parts. The imaginary parts, that's I times, well, let's leave it. The imaginary parts was ix by 1 factorial minus ix cube by 3 factorial, then the imaginary part was plus ix to the power 5 by 5 factorial, and so on. Right, now see all these terms here contains I, so we can just factor out the I here. So I can write I times, we have the series, this was x by 1 factorial, that's only x only, minus x cubed by 3 factorial plus x to the power 5 by 5 factorial, I have no space here, so on, plus so on. It would be minus so on, because the next term would have a negative sign, because this would have a negative sign. Now this term will remain as it is, that is 1 plus x square by 2 factorial plus x to the power 4 by 4 factorial plus so on. Now if you see, when I started the video, I said that two expansions about the sine and the cosine x. So let's get to that. Let's get that out, what I said about the expansion of the sine and cosine x. So see, the expansion of cosine x was 1 plus x squared by 2 factorial plus x to the power 4 by 4 factorial minus x to the power 6 by 6 factorial and so on. So let's see, it also have the same one, it should be minus over here, because see here I made a mistake. I just extremely sorry for this mistake, extremely, because I made a mistake. This is 1 minus x squared by 2 factorial, and then this term would also be minus, right? Now see, this expansion, that is the expansion of cosine of x, and this is the expansion of sine of x, right? So I just made a mistake here. You just put in the values and you can get it. Now I just made a small mistake. That is, so if we write them, then we get cosine of x plus I times this sine of x. Now we started with e to the power ix and we ended with this. So that's the Euler's formula, and we derived it using the Taylor's theorem. Now if you don't know Taylor's theorem, then I've also made another video in which I've derived the Euler's formula without using the Taylor's theorem. So I'll be uploading the video in a few days, so you need to subscribe to my channel so that you get to know about all my videos. Now I've decided that after every video I'm going to present a challenge sum that you are going to solve, and the answer I'm going to upload it in the next videos. Now the challenge sum for this video is using Euler's formula, that is Euler's formula was e to the power I theta is equal to cosine theta plus I sine theta. That is, using Euler's formula, you have to prove that cosine theta plus I sine theta whole to the power n equals to cosine n theta plus I sine n theta. And I'll be uploading the solution of this video in the next video. Solution of this sum of course not video. I'll be uploading the solution of this sum in the next video. And don't forget to subscribe to my channel, Math Oxo. So till then, meet you at the